Am I live? I am. Okay, so today what I'm planning to do is the following. Sorry. I just need to turn down my notifications. Okay, maybe now I won't be bothered. So, what I'm planning to do today is to continue learning about the deep learning in Python. So, I think the last time where I stopped is just a second. The chapter about neural networks. Alrighty. And what if I turn this on now? Yeah, we have it here. So last time I stopped here, but I did it maybe a week ago, maybe even two, so I forgot most of the stuff. So I'm just gonna do a quick recap of neural networks. So I assume the drawing of a brain here was made because the neural networks were inspired by the biological brain. But I think as time passed on, we couldn't be 100% sure how to emulate the brain because the complexity of the brain is not known even today. So we actually tweaked neural networks to fit their own perspective and functionality. All right. So what I have here, so I wrote a point about neurons. I wrote a point about how neural networks are connected using connection links and how a neuron has an activation function. All right. So a neural network is basically a mathematical model for information processing. A mathematical model for information processing. So what is this meaning? Sometimes a book can be purposefully obscure. I am reading a book on DL, deep learning, and the chapter that I'm reading right now is about neural networks. Can you explain me in simple terms? Let me just turn off my tablet. What the above sentence means. So a neural network is a mathematical model for information processing. Neural network. It's a system that tries to mimic how the human brain works. Okay. Mathematical model. Everything that a neural network does is based on math. It uses equations to represent and process information. For example, numbers go in. The neural network applies operation. So I think I kind of understand the big picture regarding deep learning and neural networks, but once I dive deep, and hopefully we will dive deep at a certain point, I think at that moment we need to start understanding advanced mathematical concepts and models. Right now I'm just doing theory. Information processing is the purpose of a neural network. Okay, so neural network uses some math and processes the data. Okay, let me turn this on again. Let me turn this guy on. So what do I have here? Information processing occurs in its simplest form over simple elements called neurons. So neurons are connected and they exchange signals between them through connection links. Okay. So what I already wrote this. So connection links can be stronger or weaker, and this determines how information is processed. And each neuron has an internal state that's determined by all the incoming connections from other neurons. And each neuron has a different activation function that's calculated on its state and determines its output signal. Okay. How am I doing this? All right, let's talk about neurons right now. Okay, neurons. So what's a neuron? It's a mathematical function that takes an input value or more of them and outputs a single numerical value. So this seems simple enough, right? It's a function. So I assume this is the neuron right here in the image. So what? These are the inputs, these are the weights, and this is the neuron that has the activation and the activation function, and then provides an output. Oh, we also have a formula for the neuron. So this is how a neuron is defined. So this is how a neuron is defined, the formula right here. And what does it mean? So what do we compute first? We compute the weighted sum of the inputs xi and the weights wi. So that's it. So we have the weights and numerical values that present either the strength of the inputs or the strength of the connections between the neurons. And the weight B is a special value called bias, whose input is always 1. Okay. And then we use the result of the weighted sum as an input to the activation function. So wait, what do we have here? So what is the activation value? Wait. I have a couple of questions here. What is the activation value in the context of a neuron? In the context of a neuron, in a neural network, the activation value is the output of that neuron after it has processed the input and passed it through an activation function. Here's how it works step by step. Each neuron receives inputs from other neurons or from the data directly. These inputs are multiplied by weights. A bias is added, and this is the weighted sum. So these are the weights, these are the inputs, and B is the bias. And now the activation function. So the sum is passed through an activation function. This function introduces non-linearity to the neurons. Okay, I still have no idea, no clue. So I'm reading something in the book that says the following. The activation value can be interpreted as the dot product between the vector w and the vector x. The vector x will be perpendicular to the weight vector w if x, the vector x times vector, so the vector x therefore all vectors x such as these define a hyperplane, the feature space Rn, where n is the dimensions of x. I have no clue what this means. All right. This is another paragraph in the book regarding so I just haven't copied it all. So this is a dot product. So the activation value can be interpreted as the dot product between two vectors, the weights vector and the inputs vector, plus a bias term B. Okay. Sorry, Teta, my best friend, you prepare group Discord again. I'm lost. Can you prepare group Discord again? I want to join you. I, I mean, uh, I could. I just, I mean, I'm streaming because I want to motivate myself to learn. I didn't know anyone was interested in watching me. But if you guys want, I, I could create it. I have no idea how a Discord works, so I would need to brush myself up on it. But yeah, if you want, why not? Good. So if the dot product is 0, it implies that the vectors x and w are perpendicular in space. Perpendicular in space. So it means that the input vector x lies on a boundary defined by w where the neuron does not activate. Perpendicular. Yeah, so basically they have a 90 degree angle between them. All right. The dot product between x and w is 0. The dot product between x and w is 0. How to calculate a dot product? I think you just multiply the first value and then you just sum it, right? How to calculate the dot product of two vectors? So it's I think this is dot product. So it's if one vector has these elements, the other one. So it's a1 b1 plus a2 b2 plus yeah, I think this is so the activation value can be interpreted as the dot product between two vectors, w and x, plus a bias term, b. So the dot product measures how aligned v and x are. If the input vector points in a direction similar to the weights vector w, the dot product will be large. If they point in opposite direction, it will be negative. So this is the activation function and this is the bias. The statement the dot product x and y equals 0 means that the dot product between x and y is x and w is 0. When the dot product is 0, it implies that the vectors x and w are perpendicular. So there's a 90 degree angle between them. So geometrically, this means that the input vector x is defined by w where the neuron does not activate. So what's a hyperplane? So it's a n-1 dimensional subspace in R, the space where x lives. For example, in 2D, a hyperplane is a straight line. Is there an example of this anywhere? Okay, so a neural network can have, an NN can have uh, layers. So we group neurons inside layers. The input layer represents the dataset and the initial conditions. So if the input is a grayscale image, the output of each neuron in the input layer is the intensity of 1 pixel of the image. All right, so yeah, if you provide an image, and let's say these are the individual pixels in the image, assume that we will have a neuron for each pixel, right? The output of each neuron in the input layer is the intensity of 1 pixel of the image. Okay. And we don't generally count the input layer as part of the other layers. When we say one layer net, we actually mean that it's a simple network with just a single layer, the output in addition to the input layer. Okay, so we don't consider, we don't count the input layer as part of the other layers. Okay, so why we don't do this? It's an agreement most probably. So when we say one layered net, there's only the output in addition to the input layer. Do we have an example somewhere, please? Okay, so we can also have multi-layered neural networks. So these are multi-layered NN. Okay. So we can introduce more layers between the input and the output, and these layers are called hidden layers. The following, okay. So there's a, okay. Okay, let me just check something. I'm gonna turn this off. Multi-layered neural networks. How do they look like? So that's a multi-layered neural network. So these extra layers are called hidden layers. So the input has how many n? Because it's x1, x2, all the way to xn. So the input layer has n input neurons. The next one, this is the first hidden layer, it has, I assume it has less than n. We don't know exactly, but let's say it has m hidden neurons, and the second one has, I don't know, p hidden neurons. And now the output has, again, more classes. It has multiple outputs from y1 to yn. Okay, I'll next time prepare group, your Discord. You can tell me, my friends. Okay, I'll try to do this again. If you want, we can all learn together. I also don't know a lot about this. Yeah, I'll remember. Let me just try to prepare, create a Discord. Okay. The worst thing is I knew all this in university. I mean, I didn't knew it well. I knew it enough to pass my courses. Oh shit! I forgot that I turned this on. So yeah, this is the image I was looking at. But now it feels like my brain is fried. Okay, so this is a multi-layer neural network. If the neurons don't have activation functions, their output would be what is this? Wait. Oops. Enjoy my wallpaper. All right, let me open this again. Let me open this again. Uh, so to be honest, the explanation from this book isn't cutting it for me. So I'm gonna try to find another explanation of a neural network. Because I like to understand the concept, the topic I'm learning, but I like it also to be explained in a way. If I don't know the prerequisites for it, I can easily grab and learn them. Here, it seems that there's a lot of prerequisites you need to know in order to learn this. You know, it's overly conceptual and mathematical. Okay, but I need more insight about this. Okay. Okay. So I don't have a PhD. So in order for me to understand this, I need to go back to the basics. So a neural network is a mathematical function that takes, the simplest explanation is, no, this is too dark. And then takes inputs, provides outputs. All right. And then consists of layers having neurons. All right. Okay, let's do this again. Neural networks. I spent 37 minutes. Not. So let's go back to the foundations, to the basics. No, I don't want this one. The basics. Okay, so these are the basics. So the first thing, the first building block of a neural network is the function. So function. So a function can have a mathematical background, described in mathematical notations. So let's say a function can be written like this, and this basically says we take a number x as an input, and we can transform it into x squared. Okay. All right. Next, we can define function in the concept of diagram. So it's another way of depicting functions. So what we need to do is to have an x epsilon plane, x epsilon, so what we do next is, okay, this may be small, I need a bigger one. This is small as well, but okay, maybe I can do x and epsilon. So what we need to do is to plot the x coordinates here, like 1, 2, 3, -1, -2, -3. Okay, let's also use -4 and 4. So we have the inputs on the x-axis, and on the epsilon axis are the outputs of the function of that range. So if we use x squared, what I have on 0, I will have a 0. On 1 squared is 1, and it's gonna be here. Also -1 squared is 1. So 2, 3, let's say 4. 2 squared is 4, so I do it like this. Same thing here. 3 is 9, so let's oh no. Yeah. So let's say 9 is here. It's not obviously, but let's say it's there for the purposes of this. So this is another dot, this is another dot, and then we connected these plotted points. Okay, in real life I don't think this graph is as narrow at the bottom as mine is, but this is only for educational purposes. So we connected the plotted points, and all right, so this is the square function actually. Square function. All right, let's continue. Okay, now the book says there is another way to depict functions that isn't as useful when learning calculus, but that will be very useful for us when thinking about deep learning models. Okay, Okay, so we can think of functions as boxes that take numbers as inputs and provide numbers as outputs. So if we have something like, what is the size of this? Is it 15? Okay, what if I put 20? So what do we have here? I have a box and provide again, and what I'm getting back is n squared. So this is the square function. And what we can do now is provide for n. 1 it's gonna be 1, 2 is gonna be 4, for 3 it will be 9, 16 for 4, and so on, so on. Now another way we can define functions is using code. So we have math, diagram, and let me just move this away. Code. And we're gonna use NumPy for this. So what's NumPy is a Python library for fast numeric operations. It's written mostly in C because we will mostly deal with multi-dimensional arrays, and it's fast and deals with calculations on these arrays properly. And let's even try it. So it's gonna be ls cd projects, no, clear. Do I have a deep learning here? No. All right. So now let me ask here how to set up a Python environment with NumPy. All right. So what does it say here? Create a virtual environment. All right, I can do this pretty fast. You are here. Python env my env, so I don't have this. I should use Python 3, right? Or maybe I should create an LIS, but maybe not now. Okay, I have it. So I can can do this, and then I think I just install it, yeah. Pip install numpy. All right. Okay, I think I'm fine. I think I'm fine. Alrighty. Should I also install the notebook? Wait, how to use? Can I use the note, the so I can also install this. Oh, I forgot the whole time that I'm okay. All right, so let's now open so how do I set this up? Wait, I need to also install the Python. Okay, let's open this. I'm just gonna increase this a bit. Wait, do I have any themes or anything here? Theme, color theme. Ah, okay, I have something. So, new folder, I'm gonna call this foundations. Let's call it chapter 1. And then I'm gonna call this foundations dot. All right, do I have the Python here? Okay. Let's also install Jupyter. All right, let's do the code now. So I can add markdown, right? Okay. Let's call this imports. Let's add code, but code I should add about this. How do I delete this? Code, why is it? What? Import numpy smp. Why does it? What does? Code. Okay. I get it now. So if I run this, Python environments, my environment, is it working? It is. All right. So let me create another code here, and let's talk about some peculiarities of what's happening here. So print, does this work? I'm testing it. Okay, so is this working? Run all. Does okay, nice. So what do we have here? I have an array that has these elements and another one that has these elements. So if I print A plus B, what will I get? I will get this, basically I will get the concatenated array, because this is how lists work, not only in Python but in most programming languages. What if I try print A times B? I get a type error. Can't multiply sequence by non-integer of type list. So I'm just gonna do a try here, and I'm gonna write here, if I get a type error, print multiplication is not allowed for Python lists. If I run all of this, okay. So this is, these are Python lists. Now here, let's talk about NumPy arrays. So if I get array 1, 2, 3, same thing here, 4, 5, 6, and if I do now A plus B, and if I try to run it all, I get 5, 7, 9. because now we can operate on these arrays as if they were vectors. So if I do A times B, I think we will only get one value here. 4, 7, 18. All right. So these are the ND arrays. And they basically the ND arrays just mean n-dimensional arrays. All right. So what are some other peculiarities of NumPy? Hi Lionel. So you wrote, "Hi, YouTube recommended this live. What are you programming? It looks interesting." So I'm a front-end dev that has been interested in deep learning as of late. So I'm trying to grasp how neural networks work. As someone who had no or minuscule interaction with it since my university days. Basically, since my university days, I haven't even looked at this. All right. So these are neural networks. So what if you create an array like this? So I have np array 1, 2, 3, 4, 5, 6. So there's not a formatter here. Why not? Do I have prettier? Oh, my bad. Why didn't I install it already? All right, can I form? Why don't you work, friend? why? Okay, just a second. Setup prettier as the default formatter in VS Code. Seems that I reinstalled VS Code, so I don't have anything on it. Okay, so what happens if I print A again? Why is this happening? Because I forgot this. All right. So are there any other peculiarities here? Let's start. No, I don't want to restart. Create a markdown here. No, I need this. I can do this over here. So wait, what if I do the following now? What if I have this array, and if I do print a sum access 0, will this work? No, because I pressed space here. Now it's gonna work. So hey all, I know nothing about neural networks, me neither. It has to do with graph theory, I guess. Yeah, as much as I understood it from today, and maybe I started a week ago, is that it's a combination of like highly advanced multi-dimensional math based on vectors mostly, and a lot of regression algorithms. So yeah, I also have no idea. I'm also learning it. So basically what I'm doing right now is I'm just testing a bit regarding this NumPy, regarding the NumPy library that I'm gonna use, and I'm looking at some tips online. So basically this command, what I think it does is summing along the 0 axis. So if the 0 axis is so let me just check what the 0 axis is. Hey Lagar, hopefully I pronounced your name right. So what I'm trying to do here, just a second. Where are you? Where are you, friend? Where are you, friendo? Here. What's this? I don't need this. Where are you? I'm looking for some. Yeah. This. So. Sorry, I had my tablet the whole time on the screen. I'm an idiot. So basically, yeah, what I wanted to do is the following. I need to open my tablet again. So let's say this is a 2D NumPy array, and we have two axes. We have the axis 0 and the axis 1 because it's a two-dimensional array. So now when we run this, sum method on this multidimensional array, what will happen is that it's gonna sum along the 0 axis. Basically, what we're gonna have is the following. So we have 1, 2, 3, 4, 5, 6. So if this is the 0 axis, so we're gonna sum this way. Basically, we're gonna sum all of these elements, and now we're only gonna have a single dimensional array that has these elements 5, 7, and 9. And if I run this here, I already run it, but you can see here sum along the 0 axis. It's 5, 7, 9. And if I do the same thing along the first axis, so what will be there? What will be there? So the first axis is, let me just remove this. This is the first axis. So we're gonna sum this way. So in this case, we'll have only 2 elements. So we're gonna have 1 plus 2 plus 3. That's 6. And we're gonna have 10 and 15, I think, right? Makes sense. 6 and 15. Okay. Okay. What else can NumPy do that regular lists don't do is just a second. Hey guys, hey all of you. All right. So these are some specific, I mean, these are basic things, but these are some specific things that NumPy does that regular lists don't do. So what else can we do here? So we have this multidimensional array, right? So what can we do now with this multidimensional array? We can add a single dimensional array of a length C, and NumPy will do addition in the intuitive way, adding the elements to each row of A. So if I do mp array, let's say 5, 5, 5, and if I print A plus B, A plus B, so what's gonna be? It's gonna add, I think, 5 to all of these. It's gonna be 6, 7, 8, and the other one is gonna be 9, 10, 11, right? 6, 7, 8, 9, 10, 11. Okay. So this seems relatively simple. So these are some kbats that NumPy does. Okay. All right, so there's another caveat, but I think this is specific to it's not specific to ND array, I believe. But it's called, let me just create maybe a new, not code, maybe a new markdown. What's a markdown? This is, can I just move it? How can I move it above this? How can I move you some? Ah, I can. No, I can't. So I'm gonna create a new markdown and then I'm gonna create a new code. Okay, so this is gonna be, this is markdown. I'm gonna call it basic functions. Now if I run this, all right. So what I'll have here is this. So I have an array. I'm gonna provide an ND array, and the response will be an ND array, and I'm gonna return this. So I need to define ND array, right? Okay, from numpy import ND array. If I run this, it should work. So basically this A, if I hover over A or B, this should be the type of ND array. What this does, and this is I think pretty common in most programming languages, at least those who have type checking, is to help you give some idea of what a certain concept is used for. Basically just gives you the type of what we wrote. If I just had wrote here, if I had wrote here this, I mean, I could guess from the simplicity of the method what it does, but what kind of squaring am I doing? If I didn't have here MP, I would have no idea I'm working with n-dimensional arrays here at all. So if I run now, okay. So I'm with type checking, we can actually understand better what is going on in this function. Okay. Okay, so these are the basic functions. This is one of them, and the other one, so I copied this from a book. This one is called Riki Relu. It's gonna be ND array. The response will be an ND array as well. So what is this one doing? Maximum 0.2 times x or x. Okay. And the good thing is that we are having these power functions that are under the umbrella of MP. So with this, we can actually apply many of these functions, like here. Okay, so this is the math. This is all at this. Oh no, have I? No, I haven't. I thought my tablet was still on, but it isn't, thankfully. All right, now let's talk about some math now. Let's talk about some math. Let's open this guy. I hope you like my wallpaper. So let's open this guy up. And let's talk about something named derivatives. Now this is a name I hadn't heard in a long time. So what is a derivative? So the simplest explanation of a derivative is that a derivative of a function is the rate of change. Rate of change, whatever this means. Let's walk through some derivative examples to understand what a derivative really is. Okay, so what's a derivative? So here it says there is a mathematical explanation for derivative. So how much the output of f changes as we change its input at a particular value of a of the input as a limit. So df over du a is what? It's a limit that goes here. It's 2 times all right. How much the output of f changes as we change output of f as we change its input at a particular value of a of the input as a limit. Okay. Just a second, sorry. So let me now open ChatGPT. ChatGPT, where are you, my friend? Here. Here. Okay. Wait. While reading a book on neural networks, I came across the concepts of a derivative. And in one of the paragraphs it said the following. Can you explain to me in simple terms what this means? So how much does something change? When the book talks about how much the output of f changes as we change its input, it's really asking, if I slightly tweak the input of a function, how does that affect the output, the result I get? So this is super important in neural networks because it helps us figure out how to adjust things like weights to make the network better. A derivative is a fancy word for measuring how fast something is changing. Oh, my tablet's on, sorry. So if I'm riding a bike, your speed at any moment tells you how fast your position is changing. The derivative of a function tells us how fast the function output changes as its input changes. But this is something that's so logical, but I never thought about it. Basically, if you're driving a car, the speed of the car is telling us how fast we are, how fast we are changing our position. Yeah, interesting. All right, let me just take a small break. I'm gonna be back. Just a second. Okay, sorry, I'm back. I just had to grab a chocolate. My sugar levels were falling. So what is being discussed here? A derivative. The derivative of a function tells us how fast the function output changes as its input changes. As its input changes. Alright, so what's a limit? Okay, the book mentions a limit because we want to measure this change very precisely. Here's why. So imagine zooming on a graph of a function. At some point it looks like a straight line, even if it's curved far away. So the slope of that straight line at a particular point tells us the derivative at that point. Okay, this makes sense. If you zoom anything deeply enough, all the curves will appear as straight lines. So this slope of that straight line tells us the derivative at that point. So how we can calculate the slope is by, I think I wrote it here. We pick 2 points on the functions close to each other and we find the change in output divided by the change in input. It makes sense. It makes a lot of sense. I think I understand it now a bit better. So we have the derivative. So this is the derivative is equal to a limit So what's this? So this is the rate of change, right? So if I do this, we can approximate the limit numerically by setting a very small value for delta. Is this called delta? I think it is. So we can compute the derivative as following. All right, so I can have this. I need to reduce the font a bit, I'm sorry. So I can fit more things on the screen. So I have this df over du of a. It can be the function of a plus 0, 0, 1 minus the function of a minus 0, 0, 1 over 0, 0, 0, 2, right? But now let's take a look at this from a diagram perspective. So what do I have? I have the epsilon axis, I have the x-axis, and let's say I have a slope that goes like this. And then I have a point here, A. So this point is, let's say, here. And it goes here, and this is f of a. F of a. Okay. Now I can create a really small point next to a. So it's gonna be, so let's assume this is really zoomed in. So this is gonna be a plus 0, 0, 0, 1. And it goes here. Then I assume it will go here. F a plus 0, 0, 0, 1. Okay, and I can do the same here for a minus 0, 0, 1. So this is gonna be a minus 0, 0, 0, 1. Bum, 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 bum. I can go here. Bum, 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 bum. I go here. So what I'm doing now is I'm connecting these dots and creating a slope. So slope is going like this. So this is the slope. Basically, this is the same as f 0, 0, 1 minus, sorry, let me just move this a bit away so I can, minus f a minus 0, 0, 1 over 0.002. So the derivative of f at this point a is just the slope of this line at a. And we can calculate this slope of this line, and we can create an infinitely small distance between this and connect these two lines. Okay, this is simple. I I learned about this in university. So okay, okay. Okay, now this asks another question, because we said here that we have the square function where 2 changes into 4, right? So what if we ask ourselves, if I increase this by 0.001, by what value will this be increased? Hey Tata, I haven't created it yet. When I create it, I will definitely send it. I will provide it. So if we pull, so if we increase the input or decrease input by a very small amount, so we are asking ourselves, by what multiple of this small amount will the output change if we know the inner workings of this factory, of this function basically. Okay. All right. Let me end this here. I streamed. Oh, I streamed for 1 hour and 40 minutes today. So, okay. I think I get concepts. I understand most of these things. I hope that the next stream will continue this, and I'll get even more things right here. So thank you, and see you in the next episode. I mean, the next streaming session.